Hey everyone, and welcome. Today, we're going to pull back the curtain on the unsung hero of our digital world, the Database Management System, or DBMS. We're going to see how these incredible systems take total data chaos and turn it into clean, organized, and super accessible information. Let's dive right in.
Seriously, think about it for a second. Your social media feed, your shopping cart, your Netflix history, all of that is a ton of data that needs to be stored, updated, and pulled up in an instant. So how does it all work without just crashing and burning? Well, the secret is the Database Management System. It's this powerful piece of software working hard behind the scenes of pretty much everything you do online.
Before we had these amazing systems, things were, well, they were a mess. Picture a giant library with no librarian and no catalog system. Books are just tossed into random piles. That's what old file-based systems were like. If you changed your address in one file, it stayed the same in another. It was a recipe for disaster, full of inconsistencies. And finding anything? Painfully slow. As the data grew, the whole system would just grind to a halt.
And that's where the DBMS swoops in to save the day. It really is like a master librarian for all your data. It doesn't just store information, it organizes it, it indexes it, and it gives apps and users a really clear way to find exactly what they need right when they need it without messing anything else up. It's the central hub that finally brings order to all that chaos.
Okay, so let's really break down this big upgrade. What is a DBMS, and why was it such a game changer for how we handle information?
At its heart, a DBMS is the software that lets us talk to a database. It's our toolkit for creating the database's structure, adding new data, changing old data, and getting rid of stuff we don't need anymore. And its whole reason for existing is to solve those huge problems from the old days, like having the same information copied in 10 different places, or data becoming totally inconsistent over time.
Now, the real revolution came with a specific type of DBMS called a Relational Database Management System, or RDBMS. Instead of just a jumble of files, an RDBMS organizes data into neat, structured tables. Think of a spreadsheet with clear rows and columns. Every single piece of data has a specific home. This simple idea made everything so much faster and way more efficient. Pretty much every database you hear about today, MySQL, Oracle, you name it, is a relational database.
So, if the DBMS is our librarian, how do we ask it for a book? We can't just use plain English, right? We need specific languages. And what's really smart is that these languages are separated by what they do, which helps protect the database from any accidents. Let's take a look at the four main types.
First up, we have DDL, the Data Definition Language. You can think of this as the architect's language. You use DDL commands to draw up the actual blueprints for your database, creating tables, saying what kind of data goes in each column, and changing that structure later if you need to. It's all about building the foundation. Okay, once the structure is built, you got to put stuff inside it, right? That's the job of DML, the Data Manipulation Language. This is the language of the day-to-day worker. You use DML to select data so you can see it, insert new records, and update existing ones. This is what you use to actually interact with the information stored in your tables.
Of course, you probably don't want just anybody to be able to see or change all the data. That's where DCL, the Data Control Language, comes in. This is your security guard. With DCL, you can grant specific permissions to users, like maybe someone can read data but not change it, and you can revoke those permissions when they're not needed anymore. Super important for security.
And last but not least, we have TCL, the Transaction Control Language. Think of this as the manager who oversees complex jobs. A transaction might involve a few different steps, like moving money from one bank account to another. TCL commands like commit make those changes permanent, but if anything goes wrong, rollback can undo the whole thing, making sure your data always stays correct.
Speaking of keeping data reliable, that is not something databases leave to chance. Nope, they follow a very strict set of rules for every single operation, a set of principles that are famously known as the ACID properties.
And this brings us to the ACID properties. It's an acronym for 4 rules: atomicity, consistency, isolation, and durability. And together, they act like a contract. It's the database's promise to you that your data is going to be handled safely and correctly, no matter what. Let's quickly go through each one.
First is atomicity. The easiest way to think about this is a bank transfer. 2 things have to happen. Money gets taken out of account A, and it gets put into account B. Atomicity says this whole operation is one single indivisible atom. If any part of it fails, like if the system crashes after the money's taken out but before it's deposited, the whole thing gets canceled. It's all or nothing. This prevents money from just vanishing into thin air.
Next up is consistency. This makes sure that any transaction always keeps the database in a valid, rule-abiding state. So, for example, if a bank's rule is that an account balance can never go below 0, the database will literally block any transaction that tries to break that rule. It enforces the rules so the data always makes sense.
Then we have isolation. On a busy website, you could have hundreds of things happening at the exact same time. Isolation guarantees that all these simultaneous transactions don't trip over each other. It's like they're each working in their own little bubble, and the final result looks exactly the same as if they had just run one at a time.
And finally, there's durability. This is a simple but super important promise. Once the database tells you that a transaction is complete or committed, that change is permanent. It's going to survive a power outage, a system crash, whatever you throw at it. Your data is safe and sound.
So we know how to talk to a database, and we know the rules it lives by. But how is it all actually put together? Well, the design of any good database comes down to two really important concepts: keys and relationships. Let's see how they create the blueprint for our data.
Keys are basically special columns that help us identify and connect our data. The most important one is the primary key. Just think of it like a unique ID for every single row, like a student's ID number. No two students can have the same one. Then you've got the foreign key. This is how we link tables to each other. For instance, a student's table might have a column for course ID. That course ID is a foreign key that points right to the primary key in the courses table. That's how we connect a student to the course they're taking.
Using those keys, we can define how different tables are related. A one-to-one relationship is pretty simple. One person has one passport. A one-to-many relationship is super common. One teacher can have many students. And a many-to-many is also all over the place. Many students can sign up for many different courses. Getting these relationships set up correctly is really the heart of good database design.
Okay, last section. Even with a brilliant design, databases need a little upkeep to stay fast and efficient. And the most important process for keeping a database clean and free of junk is something called normalization.
Normalization is basically just tidying up your database tables to avoid problems later on. The main goal here is to reduce redundant or repeated data. So imagine you had one giant table with student info, course info, and teacher info all crammed together. If a teacher changed their phone number, you'd have to find and update it for every single student they teach. That's just asking for trouble. Normalization fixes this by breaking that huge table into smaller, more logical ones. A student's table, a courses table, a teacher's table. Now the teacher's phone number only exists in one single place. This kind of organization makes the whole database faster, more efficient, and way less likely to have errors. And finally, let's look at two ways to remove data. They sound kind of similar, but they are used for very different jobs. The delete command is like a scalpel. It removes specific rows that you choose. It's very precise, but it can be a little slower. Truncate, on the other hand, is a sledgehammer. It instantly wipes out all the data in a table. It is incredibly fast, but you lose everything in one go. So the takeaway is simple. Use delete when you're being careful, and only use truncate when you are absolutely sure you want to empty a table completely.
And there you have it. From the total chaos of messy files to the structured, reliable, and efficient world of the database management system. We've seen how it's organized, how we talk to it, and the golden rules that keep our data safe. This is the foundation that almost every application you use is built on. So the only question left is what's built on top of this that you want to understand next.